All right, today we're going to work on percent yield problems, and you need to understand the nature of the problem. And basically what they're doing in these problems, you'll see that you'll have a mass of reactant, and then you'll also get a mass of product. And what they're saying is they've actually carried out this reaction in the lab. So they did the reaction and they got this much product. What your job is to calculate on paper what you would get. Because, on paper, you're assuming that every single atom and molecule find each other, recombine, and that's how much you get. But in reality, you never get what you calculate because not every single atom or molecule are going to connect. And that's one of the things. If you're working in the industry, your boss is going to be wanting to know what your percent yield is because you want it to be as close to 100 as possible, obviously. So let me show you how to do these problems. Now, the thing is the actual yield, this number right here, this is always going to be given in the problem. Now, how are you going to identify it? Because it's a yield. It's got to be it's got to be a product in the reaction. And then what you're going to do is you're going to calculate what you get in theory, divide it into that number, and then multiply by 100, and that'll give you the percentage that you got based on what you should have gotten if every single atom and molecule hit. So first of all, we need an equation for this. So it's calcium carbonate is decomposed. And again, you guys are that's the one thing I worry about this year. You need to know calcium is 2, and you need to know what carbonate is. It's CO3 with a -2 charge, and so it's CaCO3. Decomposed to produce calcium oxide. Again, we do cross the charges to put those together, but they are 2 and 2, so they cancel out. And carbon dioxide, now that's a molecular compound, 2 nonmetals, don't cross the charges. The di means there's 2 oxygens. It is a balanced equation, so we can move on from that and do the problem. So again, I'll move that equation over here again. So CaCO3, should have done that in the first place, but CaO plus CO2. It's actually balanced already, but don't need to do anything to balance it. So 24.8 grams of calcium carbonate is heated, and 13.1 grams of calcium oxide is produced. So that means that number right there is our actual yield. So I'm going to put AY, that means actual yield there is 13.1 grams. What you have to do is calculate theoretically how much you get. So you're going to use the reactant that you start with, just do a normal stoichiometry problem to calculate how much you should get if every single one of those molecules broke apart and we got the maximum amount of product, and then you're going to divide it into that number. So again, it just becomes a regular problem. So we use our reactant, 24.8 grams of calcium carbonate. Remember, when we're doing any stoichiometry problem, the first thing you do, if you're not in moles, convert to moles. So you got to go to moles of CaCO3. And remember, whatever unit you start with is the unit that goes in the denominator of our first conversion factor. We would say that 1 mole of calcium carbonate, again, is how many grams? Calcium weighs 40, carbon weighs 12, 3 oxygens weigh 48. So that's 100 grams is what that weighs. And then, so this gives us moles of what's given. Then we always go to moles of what we want. We get these from the balanced equation. There, we're going to calcium oxide, so we need moles of calcium oxide, again, over moles of calcium carbonate. And again, this middle step in stoichiometry, you always get those numbers. It's the ratio from the balanced equation. So there's a 1 in front of calcium oxide and a 1 in front of calcium carbonate. Now again, so what this tells us here is that however many moles of calcium carbonate we get, let's say you get 0.2, we're going to get 0.2 moles of them because it's a 1-to-1 ratio. That's what that allows us to do. And then when we're done, we need to know how many grams of calcium oxide we're going to get. And again, we got to cancel out our preceding units. So calcium, 1 mole of calcium oxide, that weighs 40, that weighs 16, so it weighs 56 grams total. And again, we'll work out and see how much we actually get there. So work it out and multiply, cross, and divide. You end up with 13.9 grams of CaO. So that's 13.9 grams of calcium oxide. Take that number, that is theoretically how much we should have gotten, and divide it in what they said they got in the lab. So 13.1 divided by 13.9 times 100 to make it into a percentage. And in this case, we got 94.2% of what you should have gotten And you go, well, what's a good number? What should you get? Your boss would tell you that, what's acceptable and what's not if you're working for some company. All right, moving on to the next one. We've got iron oxide reacts with an excess of carbon monoxide. So again, we got to cross the charges and put those together. It's iron 3 oxide, so the charge of that is 3. The charge of oxygen is 2. Cross the charges, you get Fe2O3. Carbon monoxide, again, that's 2 nonmetals, no charges to cross there, so mono means one oxygen. Produce a molecule of carbon dioxide and iron. Remember, any element by itself, you don't consider its charge, you only consider is it diatomic or a Brinkloff element, and it is not. We can go through and balance this. We end up with 3, 3, and 2, which would balance that. Again, you can double check it all to see that it's balanced. Remember, it's it says when 84.8 grams of oxide or iron oxide reacts with excess, don't worry about the excess, doesn't affect the problem. Carbon monoxide, you're going to get carbon dioxide, and 54.3 grams of iron is produced. So that 54.3 grams, again, that is the actual yield, is what that is. So that is the actual, that's just AY, and it is 54.3 grams that is produced of iron. And again, I should have listed up here what this was. So this is calcium oxide is what we're solving for there. So you're going to solve for how many grams of iron you get theoretically. It'll be theoretical yield of iron. It's just a normal problem. You're just solving for how much iron you'd get on paper. It's in theory. So you got 84.8 grams of Fe2O3. Again, we're not in moles. Got to go to moles of Fe2O3 because, again, the relationship in the balanced equation is a relationship in moles. This tells us that 1 mole of iron oxide is going to get us 2 moles of iron. So, again, we've got to say 1 mole weighs how many grams? Iron weighs 56, so 56 times 2 is 112. 3 oxygens weigh 16 times 3 is 48, so that's a total of 160. And then we're going to go with moles of iron. Again, this is moles of what's given. We always got to go to moles of what we want. Cancel the preceding units. Cancel the preceding units there, so Fe2O3. Again, we get these numbers from the balanced equation. You see that 2 moles of iron is produced by 1 mole of iron oxide. So that gets us the amount of iron oxide we have, and then we got to multiply it by 2 because, if we get 1 mole of this, we're getting 2 moles of that. If we get 2 moles of this, we're getting 4 moles of that. And then we want the answer in grams, though, so now we got to go to grams of iron. Cancel preceding unit. 1 mole of iron is 56 grams. You can look that up from the periodic table. That's what it actually weighs. Multiply across there, and you will get 59.4 grams of iron produced. Take that number and divide that into what they said they got in the lab. They only got 54.3. We're saying they should have gotten 59.4. Divide those two, multiply by 100, the percent yield there, 91.4%. And again, that's how to do percent yield problems. And again, if you go, how do you know it's going to be a percent yield problem? They're always going to say, what is the percent yield? So it's not going to be a mystery there. Good luck.